Okay, let me just start by quickly summarizing what we discussed yesterday. We first arrived at the FLRW line element. And then we talked about geodesics in the FLRW metric. And in particular, we talked about photons. And we arrived at this relation, W is 1 over A, omega is 1 over A, omega being the frequency of the photons. And I mentioned that leads to the notion of redshift. If you recall, the redshift astronomically is defined as lambda emitted, the original frequency, minus, lambda observed minus lambda emitted by lambda emitted. And that is lambda naught by lambda E minus 1 Z, or 1 plus Z is lambda naught by lambda E. And the frequency and lambda are, inversely related to each other. So lambda emitted by omega naught, okay, omega emitted by omega naught. And remember, if this is, if you use that relation, what you obtain is A naught by A emitted, okay? So O is observed, okay, but A naught is A subscript naught, okay? And what it essentially implies is that, when you receive light from a faraway source, okay, and it comes from an earlier time when the scale factor was smaller, so AE is smaller than A naught, and therefore this is always greater than unity, and therefore redshift always goes from 0 to infinity. 0 corresponds to today, and infinity corresponds to Big Bang. Okay, all right. And cosmologists often use different, time or redshift equivalently. The late time cosmologists use often redshift to denote the different epochs. And you can immediately, for instance, determine the redshift at the time of decoupling. Okay, I will not have time to discuss decoupling in detail, but I have indicated when decoupling occurs. I had indicated T decoupling, the temperature at decoupling is like 3000 Kelvin, right? Sorry, 3000 Kelvin. And T today, T naught is like 3 Kelvin. And therefore, you can immediately determine that Z decoupling is roughly like 10 power 3 or so. In fact, if you calculate it exactly, it happens at a redshift about 1100 or so. It is not instantaneous. It is spread over about, redshift of about 80 or so. Okay, you can read in some of the textbooks. So next, we went on to discuss the dynamics, okay, of the FLRW universe. Okay, and we arrived at, importantly, this equation, h squared by h naught squared. We introduced the cosmological parameters, which was written as omega nr naught a naught by a cubed, right? Plus omega r naught a naught by a power 4 plus omega lambda naught minus, if I recall right, what do I have? Omega naught minus 1 a naught by a whole square. And we talked about the cosmological parameters. These cosmological parameters are these objects here, right? So what you have is cosmological parameters. Right? And one of the cosmological parameters we talked about is, h kilometer second inverse megaparsec, the value of h naught. The Hubble parameter, the value of the Hubble parameter today, h subscript naught, is called the Hubble constant. And we saw how this is like 67 something from the from the Planck data. And I also indicated values of some of the other quantities. And, so I already mentioned values of omega c h squared, omega b h squared, how, for instance, omega k minus 1, modulus of that, which we call as omega omega naught minus 1, which we call as omega k, is very small, okay? If I recall 0.055, less than or equal to 0.05 or so. So the universe seems remarkably flat. And this allows us to construct a quantity which is called the Hubble radius today. Okay, I'm not repeating for want of space on the blackboard. I'm not repeating the numbers here. I've already indicated those numbers in my previous lecture. It's called the Hubble radius. Okay, so I would urge you to calculate this. Okay, H naught inverse, right? So H naught, as we discussed, has units of inverse time, and therefore H naught inverse has units of time or equivalently length. I would urge you to calculate this number. If I recall correctly, it's about 3000 H inverse megaparsec. Okay, I hope I get this right. 3 times, yes, let me get that number correctly. Just give me a minute. Right. Okay, that's correct. So, or if we approximately, it's like 10 power 4 megaparsec. And I presume you know what a megaparsec is. Megaparsec is 10 power 6 parsec, and parsec in turn is about 3.26 light years. And I talked about the scale of homogeneity yesterday in my overview lecture. Do you recall what is the scale of homogeneity? Do you recall? Something like 100 megaparsec or so. So this leads to a scale of about 10 power 2, 100 megaparsec, close to 100 megaparsec. And, this leads to a scale of about, in wave numbers, 10 power minus 2 megaparsec inverse. That is an important scale, as we will discuss very soon. So cosmological scales correspond to roughly something like, I will write it here, cosmological scales. Therefore, correspond to, people typically talk about 10 power 4, in case about 10 power minus 5. That's a stretch, okay? This is 100 megaparsec. People push it to smaller values. And this is why, when we plotted spectra over the CMB scales, okay, primordial spectra that lead to CMB spectra, CMB angular power spectra, we talked about scales of this type. These are the large scales. When I say large scales, or generically people talk about large scales, these are the scales one talks about, okay? This is where the CMB begins to become ineffective. It doesn't constrain the primordial physics. Then there is large scale structure, something spectral distortion, and then non-trivial physics involving gravitational waves, etc., that I talked about towards the end of yesterday's lecture. So we talked about the cosmological parameters. We talked about the dynamics of the FLRW universe. It's about solving this equation. And we saw that, for instance, in radiation-dominated epoch, A is T power half, and matter-dominated epoch, A is T power 2/3. Okay, so what you essentially have is A is T power Q, where Q is less than unity. Okay, this is something you need to keep in mind. So now we move on to the next topic. And what we want to understand is to why we need inflation. I haven't touched everything that I need in background cosmology. I will come back to those topics which I need as we proceed with the lectures. Now, what we are interested in now is in the evolution of the Hubble radius. I talked about the Hubble radius today, okay? There are some relationship to a causally connected region called the horizon. Hubble radius has a connection to that. I will talk about that connection too as we proceed. So we just saw that H naught inverse is the order of 10 power 4 megaparsec. Okay. What we would like to know is, how does this Hubble radius, you can think of it as a size of the causally connected region today. And we would like to know how it evolves. and during the radiation and matter-dominated epochs. This is the value today. So we are going to define something called the Hubble radius. Maybe one should use R subscript H, Hubble distance or Hubble radius. Okay, this is A dot by A inverse. Okay, this is the Hubble radius at any given time. And remember, we are largely interested in the matter-dominated and the radiation-dominated epochs. Okay, and we will not talk about late time acceleration. We will need early time acceleration, which is inflation. All right, we will come to that. So in both these cases, how does the Hubble radius behave? Both these three cases, notice this behaves as A dot by A behaves as T, not surprising. Okay, T star, H inverse A dot by A is what? Is T power Q, right? So some of you seem surprised. A dot is what? This is equal to, is proportional to, okay, actually it's equal to, because the constant, let us say this is A naught T power Q. Okay, A naught as, okay, I shouldn't use A naught because A naught refers something else. Let me call this A1. A1 as dimension full. Please note that. Okay, so this is Q A1 T power Q minus 1 divided by A1 T power Q inverse. Okay, so what is this? This is just T by Q. That's all I meant. Okay, and now if I write in terms of A, what is it? It is proportional to A power 1 over Q. This is what I want you to recognize. So the Hubble radius dH, right, during matter domination behaves as A power. What is Q in matter domination? 2/3. Okay, so it behaves as A power 3 by 2, and during radiation domination, dH behaves as A square. This is what I want you to understand. Okay, now I need to introduce an epoch called equality. Okay, and it essentially means radiation matter equality. What does this mean? This is the epoch, this is the time or the redshift at which the energy density in matter equal that of energy density in radiation. Okay, so how does the energy density of matter go? Okay, remember we use the notation R and R. It is A naught by A whole power 3. Okay, and the radiation went as rho n R. So, sorry, rho R, A naught by A whole power 4. Okay, the epoch when these are equal is called the epoch of equality. AEQ, A subscript EQ. Yeah, okay. And I hope, I can write, there are times when it is useful to have the Hubble parameter in terms of redshift, and that you can immediately do so, right? What is this? This is just 1 plus Z whole cube. This is 1 plus Z whole power 4. And this is 1 plus Z whole square, and so on. So you have H as a function of redshift. So lecture 3 is, it's essentially about inflation, right? Driving inflation with scalar fields. But before all that, we need to understand why we need inflation. And in order to do so, we will try to understand, I will explain this more as we proceed, what is the scale that enters, or depending on whether you go forward or back, leaves the Hubble radius at the epoch of equality. That's what we are interested in. Remember, this is matter radiation equality. You can construct something called matter lambda equality. I will let you determine the redshift at which that happens. So now this is the equality epoch, and what do you have? This corresponds to, this is cubed, this goes, and what is A naught by A equality? It is 1 plus Z equality, right? That's the redshift at which equality occurs. Now, remember, we learned to write it in terms of cosmological parameters. That's the values, we know the values of the cosmological parameters. So what do? I divide by rho C naught on both sides, right? And then multiply by h squared, right? Is that correct? Okay, no, I'm sorry. I multiply by h squared on both sides, that's all. I multiply by h squared here. So what is this? This is omega nr naught, and this is omega r naught. All right. And that tells me what's the value of the epoch of equality. So if I know omega nr naught h squared, right, divided by omega r naught h squared gives me 1 plus zeq. Okay. All right. So I indicated what are the values suggested by the CMB data for omega nr naught. I can take it from there. And this, I will write it down again in a minute. And what is omega r naught? Yesterday, I asked you to do this exercise where you take into account the energy density to the radiation. It's thermal in nature. So you can use the Stefan-Boltzmann's law to calculate this quantity. I indicated a number yesterday, but to be precise, I also mentioned we need to take into account both radiation and neutrinos. Okay, if you take both of them into account, that value is slightly different from the value that I mentioned yesterday. So let me mention the complete value. Just bear with me. Right. The total value of omega r naught h squared, accounting for neutrinos, is 4.19 into 10 power minus 5. Okay. We will derive the neutrino temperature. Okay. It is 4 by 11 power 1/3 of the photon temperature, if you wish to know. Okay. I will explain the reason for it much later. Okay. When I discuss reheating, I'll just complete a few remarks and come to you. Okay. So this is what it is. You plug in those numbers, and what you find is the following. You find that 1 plus ZEQ is about 3,400. Okay. This is the epoch of equality. This is the redshift at the epoch of equality. I will let you plug in the numbers I had. Okay, I need to mention what is omega nr naught. Just give me a minute. Okay, so this is a sum of, these are the two numbers I mentioned, 0.0222 plus 0.1199. This is the Planck 2015 data. Okay, so I would urge you to estimate this number. Now, what I'm interested in showing is that many scales of interest, a considerable fraction of the scales of interest, are outside the Hubble radius at early times during the radiation dominated era. Okay, what is the scale am I referring to? Much later, we will do something called perturbation theory. I have already mentioned how to understand our universe, we are going to divide it into two parts, a background or a homogeneous part, and the perturbation part. And the perturbations will be governed, we'll carry out linear perturbation theory. They will be governed by linear differential equations, partial differential equations, which involve space and time. But I can Fourier decompose this, much like you will Fourier decompose a field, describe a quadratic action in a smooth and homogeneous and isotropic background. For instance, in Minkowski, how do? You Fourier transform and study each mode. It's just that because of the time dependence, there is a more complicated behavior of each of these modes. And that's what perturbation theory is all about. So I can Fourier decompose, and as you know from free field quantum field theory or classical field theory that you may have learned, okay, in Fourier space, these modes evolve independently. And when I talk about a mode, I'm talking about the wave number of one of these modes of these perturbations. What perturbations am I talking about? What am I talking about? It could be anything. It could be scalar perturbation, tensor perturbations, magnetic fields. It could be anything that may be of your interest. Okay, so what one finds is that all the scales, a good fraction of the scales of cosmological interest, are well outside the Hubble radius at early times. So we know that the Hubble radius at the time of equality, we know from 1 plus ZEQ, we can calculate the Hubble radius, okay? And what we would like to know is that, what is the wave number or the wavelength of that mode which equals the Hubble radius today? Because one of the things you should remember is that when people talk about scales, they talk about the scale today, okay? And that is the exercise. We are going to do that. And we'll find that we will call something called K equality, right? Again, this is the wave number that equals the Hubble radius at the time of equality. I hope you understand what is equality now. And that happens to be about 10 power minus 2 megaparsec inverse. What it implies that all scales which are, I should be careful now, the larger scales enter the Hubble radius at later times. All the smaller scales enter the Hubble radius at earlier times. But importantly, all scales are outside the Hubble radius at sufficiently early time. And what have I said? The Hubble radius is a causally connected region. Okay, if the scales are, you are introducing, this is a causally connected region, and you are trying to introduce perturbations in the early universe. There is no way you can do in a causal manner if the scales are outside the Hubble radius. And this is one of the motivations for inflation. This is the time for you to ask the question. That is correct.
So the thermal relic of neutrinos, as far as I know, has already redshifted, and the neutrinos have become non-relativistic now. So is it justifiable to include them in the radiation part?
No, why have the neutrinos decouple? Once they decouple, they don't interact with anything, okay? And they are relativistic today because their mass is extremely small. There is a constraint, I don't recall the exact number today, on some of all the neutrino masses.
The mass is small, but the kinetic energy is also small, and I think they are of the same order.
Okay, I am not able to comment about this immediately, but I believe they are relativistic, and you need to take that relativistic energy into account. Okay, so I need to look at my notes and comment about it, but they are relativistic, and it is, I wrote a number like 2.48 for photons. The remainder is due to neutrinos, and you need to account for that carefully. Okay, all right. So So I have a request. If there are questions that will not permit me to go, something you don't understand as I go forward, it's best to ask now. The other questions I'll be glad to answer at the end or during other discussion.
How did you know that Hubble radius is the size of the causally connected region?
It gives me a scale, okay? What is the quantity that tells me, what's the quantity that describes my Friedmann universe? Let us say, take the spatially flat case. What is the quantity that describes the Friedmann universe?
The scale factor.
Scale factor. If I take A dot by A, it gives me a scale. That's it. All right. And that tells me is some rough time scale. And I need to answer it more clearly, but I don't have time. So I need to calculate something called the horizon. Okay. I need to calculate something called the horizon, which will formally provide me the causally connected region. And you can show, I will leave this as an exercise to you, okay? For T power Q, unfortunately, I erased that, okay? For T power Q, Q less than 1, the horizon, I haven't defined that. I will define sometime, or I will give it to you, I can speak to you later, okay? Is proportional to the Hubble radius, modulo constant of order unity. It's only when you have inflation, they differ significantly. And I will talk about that as we proceed. Okay. So this reasonable to assume the Hubble radius to be the causally connected region because it is the same as the size of the horizon when in say t power q with q less than 1. Okay, with q greater than 1, there is something interesting I will talk about, and that's why we have the epoch of inflation. So let's carry on with this exercise that we need to do. And before that, let me plot a curve to indicate what we are looking at. So I'm going to plot logarithm of lambda of the physical radius or logarithm of the Hubble radius. I'm sorry, physical wavelength of the perturbations. Remember, if you look at the Friedman metric, how was this? It is ds squared is minus dt squared plus a squared t dx squared. Remember, all physical radius are multiplied, all physical lengths are multiplied by the scale factor E. So the wavelength of the perturbation lambda is always proportional to the scale factor. The x-axis is time. In fact, we will write time in a particular unit, okay, in a particular way. It's logarithm of a, n, with some normalization. We need not worry about it at this stage, okay? All right? So logarithm of a, and this n is often referred to as e folds. Okay, because you can write a as e power n. And now, what do we need to do? We need to plot these two quantities, and let us say this is the epoch of equality. Okay, this is the epoch of equality. That's where you have a equal to aeq. And I'm going to plot the Hubble radius. It's a log-log plot, and the Hubble radius will be a straight line because the Hubble radius is a squared or a power 3 by 2. So what will happen? It will have slopes of 3 by 2. I hope you recognize this is the radiation dominated era. This is the matter dominated era. It will have slopes of, okay, this has to be sharper. Okay, this is supposed to be a slope of 3 by 2, and this is, they are so slightly different, it's difficult. And then I have to draw another line which is a slope of unity. It's always difficult. Okay, 1, 1.5, and 2. And what do I have? So I'm going to draw just one line. Okay, this is the line. So let us say this is the Hubble radius at equality. Okay, what we are interested in, maybe I should, these are the Hubble radius, these lines which are, this is a slope of 1, right? This is slope of 3 by 2. Yeah, it's consistent. This is slope of 2. Okay. And what I'm interested in asking is, what is the wavelength or the wave number of this today? This is A naught. And I'm going to ignore late time lambda evolution, etc., lambda dominated evolution, etc. Okay, so let's do this exercise. Now, what do we need to do? We need to first calculate what is H equality. Okay, H equality. Oops, I'm going to assume kappa equal to 0, spatially flat universe. And H equality squared is what? H naught, no, what do I have? Yes, H naught squared into what? We have two contributions, right? I erased that equation. Please look back at that equation. We are going to ignore the effects of omega lambda naught. We are going to omega naught equal to 1. So that term goes away. There are only two terms, but they are equal. Okay. So because it's equality. So what do you have? You have 2 omega. I can write this as omega nr naught. Okay. I hope this is what it is. Times 1 plus ZEQ power 3. Is that correct? This is what H equality is. And what I need to do is that I need to evaluate this today. Okay? All right? So K equality or lambda equality, let me call this as, K equality is just 1 over that. We ignore factors of 2 pi. We don't worry about that. Okay? So what is lambda equality? It is H equality inverse, right? That's the size of the Hubble radius. I hope you recognize that. This line with a dash on top of it reflects the size of the causally connected region at that time. Okay? And it behaves in this manner. What we are trying to see is that So when a wavelength which evolves like this, which a slope of unity in a log-log plot, when you say when it comes inside, it enters the Hubble radius. Okay, all right. It is outside the Hubble radius here or everywhere here, and it is inside the Hubble radius at late times. Okay, and we are trying to ask what is the wavelength today that is equal to the Hubble radius at the epoch of equality. Okay, so the lambda equality today, okay, lambda equality, it happens to be H inverse times, I have to scale it by the factor it has gone up, okay, which is A naught by A equal. So I will let you calculate this. As you can imagine, you can write it in terms of the cosmological parameters, okay, and you can estimate what that is, all right? And so that I should be precise, lambda equality today happens to be, right, okay, H naught inverse equality, A naught by E equality. So I will write the final expression. You can write this as follows, okay, root omega R naught H squared, okay, by square root of 2 root omega R, sorry, omega R naught, omega N R naught H squared, okay, 1 over H naught by H. All these quantities you know, okay, all right? And therefore, what you obtain, this number happens to be 96.6 MPC, or, okay, or often you will hear that KEQ is 10 power minus 2 MPC. Okay, remember, I just wrote a length of scales which correspond to cosmological scales in a couple of boards back, which corresponded to something like 10 power minus 4, 10 power minus 5 to scale of about 1 megaparsec inverse. And this falls right in the middle. And what you find is that scales which are larger than this enter, I have to draw lines which are, sorry, which have slope of unity. It's always a challenge, right? So some enter during the radiation dominated era, some enter during the matter dominated era. And if you are careful to account for the lambda domination, some may enter during that epoch too. And this is much smaller than the largest scale today. What is the largest scale today? Okay, which is H naught inverse. That's of the order of something like 10 power 4 megaparsec inverse. So this range of scales from 10 power megaparsec, okay, all right. So scales between 10 power minus 4 megaparsec inverse, I will always talk in terms of K, okay, and 10 power minus 2 megaparsec inverse enter during the post the epoch of equality. And all other scales enter the Hubble radius during the epoch of radiation domination. Now, there is a problem. If this is your causally connected region, if this dashed line is your causally connected region, and all these wavelengths are outside the causally connected region, how do you generate perturbations on those scales? This is essentially a statement of the horizon problem. I'll come to you in a minute, Abhishek. This is essentially a statement of the horizon problem. And inflation is required to overcome this horizon problem. Okay, so what you want is that you want a sufficiently early epoch when all these modes are, complete the statement for me, inside the Hubble radius. That's what it is. And this is what inflation achieves. Abhishek. That's it. This is, that's just an English way of saying, words to describe this thing where it comes in. That's it. That is, at this point, the physical wavelength is smaller than the Hubble radius. At this point, it's greater than the Hubble radius, larger than the Hubble radius. That's all there is to it. Is that clear? This is a good point for me to stop and answer one or two questions. Yes. One.
What was special about those values?
It's 10 power minus 5, we just pushed it, often to integrate, to calculate the CLs from a primordial. Remember, I'm going to talk about power spectra generated during inflation. And if you want to numerically integrate, it's safer to integrate from 10 power minus 5 to arrive at the angular power spectra. So it's a bias of inflationary theories. You can as well start at 10 power minus 4. Okay, 1 megaparsec is where around that time between 10.1 and 1 megaparsec when the CMB stops being effective in constraining the primordial power spectrum. Thereafter, there is a narrow window over which large scale structure can take over. Okay, so that's why we are interested in those scales. That is, we will extend beyond later. There was another question. Yes, Khan. The lambda?
The wavelength.
So it's very simple.
Where are we exactly
I hope you
calculating
understand.
from you said we have that at epoch of equality, and then we calculated today. So how is that determining our horizon, or like not horizon, like causally connected region? Like, can you explain that once more?
I already mentioned why the Hubble radius indicates a causally connected region. It is the size of the horizon. In all these cases that we have studied, it's the size of the horizon. Okay. I'm wondering whether I should take a few minutes to describe the horizon, but I'm really running behind time. Okay. So I will try to see what I can do to make up for that. Okay. So Hubble radius, take it for granted for now, is the causally connected domain. Okay. So, and I presume you understand what I mean by a wavelength of a perturbation. I have explained what that is. Okay. So if the wavelength is outside the Hubble radius, okay, so there is a causally connected region, and there is a perturbation, which is, think of this as a causally connected region, and the wavelength of the perturbation is like this. What kind of initial conditions can you impose? You don't know what to do with it. Okay, how to impose initial conditions. But if it is like this, well, inside I know what to do. Okay, and this is essentially the horizon problem. All the wavelengths, a good fraction of the wavelengths are well outside the Hubble radius, at a sufficiently early epoch. Okay, and we don't know what initial conditions to impose. And if you can create an epoch where they are inside the Hubble radius, okay, you can impose well-motivated initial conditions. This will become clear when I discuss quantization of the perturbations much later. Okay. If you have studied some quantum field theory in de Sitter space-time or something like that, you will be able to appreciate it. Okay. You are not able to impose well-motivated initial conditions when this wavelength is much larger than the size of the causally connected region. Or in other words, there is no physical mechanism you can think of that can do something on much larger scale. There is no causal mechanism that can do. Okay. You expect a causal mechanism to influence the causally connected region. Okay. That's the horizon problem. Maybe one more question before I proceed. I said that is what I have written here. Slope 1, slope 3/2, and slope 2.
No, I'm saying like you have drawn 3 different lines with slope 1. What is the main difference?
They correspond to different wavelengths. That's all.
Wavelengths
or wave numbers, right? This has a larger wavelength than this, and this has larger wavelength than this. So let us say lambda 1, lambda 2, lambda 3, all evaluated today, okay, in terms of today. So these correspond to 3 different wavelengths or wave numbers with different values of wave numbers. That's all.
And how are we measuring those, like from CMB power spectrum?
No. These are just wave numbers. There is nothing to measure as of now. Okay, you understand? They correspond to different scales of observations. That's all. Okay, all right. And some of them we'll measure using CMB. Some of them will try to constrain using gravity waves. We will understand that as we proceed. For the initial part, we will focus on what happens during the first half a dozen lectures. We'll talk about only large scales, which correspond to which I've been repeating, like 10 power minus 5 to about 1 megaparsec. Okay, so let me proceed. So how do you overcome the horizon problem? It's simple. So what do I need to do? So as you go back in time, the wavelengths of the perturbations turn out to be larger than the Hubble radius in the scenarios we have discussed. Okay, so the wavelength of the perturbation, the Hubble radius, right? As you go back in time, if this ratio can decrease, okay, as you go back in time, minus d by dt, if it is less than 0, you can ensure that there is an epoch when the wavelengths are inside the Hubble radius. Is that clear? That's all, nothing more. Now, what is lambda p proportional to? It is proportional to A. What is dH? dH is A dot by A inverse. So which is A by A dot? Okay, so divided by A dot minus d by dt is less than 0, or minus A double dot is less than 0, or A double dot is greater than 0. That's it. This is why you need inflation, nothing more. If you can ensure that, okay, you can ensure that there is a period when they are inside the Hubble radius. So I have to replot that figure that I had. There is nothing more. Now let's just test, okay? I'm going to erase this, okay? I hope it is clear. So let me explain each of the terms. As we go back in time, this ratio has to decrease. Okay, or as you go forward in time, this ratio has to increase. I removed the minus sign, greater than 0, they are all equivalent. So if you have an epoch of accelerated expansion, you can overcome this difficulty, which we have referred to as the horizon problem. So inflation is easy to understand, the need for inflation. Now, let's understand how inflation resolves the horizon problem. Okay, so what do? First, let us consider A is T power Q, right? During matter and radiation domination, what was Q? It was less than 1, okay? So what do you want here? You want A dot is proportional to Q T power Q, and A double dot is Q minus 1, you should correct me. Q minus 2. What is the range of Q here? If I have A is T power Q, I have a Friedman model with A T power Q. What is the range of T here? When is the Big Bang? T equal to 0, and T can go all the way to infinity. So you are interested in the range, T goes from 0 to some value, let me say infinity. Okay, all right. So what do I need for A double dot greater than 0? Q greater than 1. T is positive, Q greater than 1, as simple as that. So radiation and matter domination are not accelerated expansion. It's not surprising. And it's clear that if I have sources which are radiation and matter, I cannot achieve accelerated expansion. This is the other part of it. Now, what is dH in T power Q? It's the same, right? Okay, so what will be the slope of log dH as a function of A? If I plot, log dH as a function of A, there may be a y-intercept we are not worried about. What will be the slope? Plus some constant we are not worried about. What will be the slope? We calculated this. What was the slope? It was 1 over Q. Why is there such silence? Right? A dot by A is Q by T. Right? Is Q by T, or it is proportional to A power 1 by Q. Okay, so when I plot log dH versus log A, the slope is 1 over Q. That's why you had a slope of 3 by 2 and 2. Okay, now if Q is greater than 1, what happens to the slope? Notice it doesn't have a steep slope. If Q is less than 1, and if, in particular, we will see you need Q to be very large, you need almost exponential. That's what slow roll inflation is. Q needs to be rather large. Okay, so the slope is incredibly small of the Hubble radius. Or in other words, the Hubble radius remains almost a constant during inflation. That's the point. Okay, so what do you have? So if I introduce an epoch of inflation, right? So I'm plotting the same quantity, logarithm of A, okay? But there is, I need the Hubble radius somewhere here. This is radiation domination. Now, during the early stages, I introduce this epoch called inflation. So I have logarithm of logarithm of lambda p and logarithm of dH, okay? So this is slope of 2. Let me draw it more steeply. Okay, this is during radiation domination. This is the Hubble radius. This is the line that I had drawn. Okay, and what is it during inflation? It's going to be, so I hope you understand. There was a big bang, right? There was supposed to be radiation dominated era. During the early stages of the radiation dominated era, I thrust in an epoch which I refer to as inflation. And during this period, okay, the slope, it has the Hubble radius has a very small slope. Okay, this is DH. So now, if I plot lines of slope unity, this is slope is 0, right? And this is slope of 2, and I can draw lines which have slope of unity. I can draw many lines like that corresponding to different wave numbers. And you have to understand that, let me draw an inset here, okay? So you have, something like this, something like this, something like that, and then there is a lambda which is flat, okay? And there is a line which goes like that, okay? And these are the wave numbers of these perturbations today, okay? I'm sorry, I have to draw that small thing, log lambda p, dh, log a. So you have inflation, radiation domination, matter domination, lambda domination, etc. And that's what it is. That's the wavelength of the perturbation. And that line inside is supposed to be the Hubble radius at different epochs. Okay, I would urge you to put in the numbers and actually plot that. Okay, take the cosmological values of the cosmological parameters, plot that quantity, plot various wavelengths, you will understand. And something I want you to understand is that, so I have to track this and it'll be somewhere here. That'll be the wavelength of the perturbation today. I hope you understand when I extend this graph. I'm not able to do so. Okay, all right. Just 1 minute first. All right. And so what do you want? You want to ensure that the longest wavelength today, right? There is often a misconception about what should be the duration of inflation. This is a good time for me to clarify. What do you want? You want all your observable universe to have emerged from a causally connected region. So what do? You take in this inset the largest wavelength today. What is that? The 10 power 4 megaparsec, right? You plug that back and you ensure, if this is my largest wavelength, say, right? Okay, if this is my largest wavelength, you want to ensure that is sufficiently inside the Hubble radius. So people don't count the duration of inflation from the start. They count the duration of inflation from the very end. Someone asked me about a pivot scale. If they are still online, it just, it's often said to be a scale which leaves around 50 folds or so from the end of inflation. Okay, you choose a scale, you set that scale to be about 5 times 10 power minus 2 or so, or 2 times 10 power minus 3, depending on, the data. It is related to the data, how well they know the amplitude at a given location from the CMB data. Okay, and you count this duration. So the duration of inflation is counted from the end. And I talked about an epoch of reheating. It's supposed to occur somewhere here. Okay, and we'll talk about that later. And there is some uncertainty when a given mode left the Hubble radius because we don't quite know what is known as post-inflationary dynamics. So let me just quickly summarize this part. I hope you understand why, why you need inflation. It was not difficult to understand. You need the wavelength of the perturbation to be inside the Hubble radius. Otherwise, quantum mechanically, you don't know. You are saying that the perturbations generated from the quantum vacuum, okay? And you essentially don't know how to impose well-motivated initial conditions on your quantum fluctuations if they are not inside the Hubble radius, okay? And inflation, I hope you understand why we need an epoch of inflation. If we have an epoch of inflation, as we shall see later, you will be able to impose what are known as Bunch-Davies initial conditions, which are like Minkowski initial conditions. So you're on small scales compared to the scale of curvature. Remember, you are on a small piece of a sphere, like the surface of the Earth. The curvature doesn't play a role. And therefore, you can treat it like Minkowski spacetime or Euclidean spacetime on the surface of space on the surface of a sphere. Okay, and you can impose Minkowski-like initial conditions, and there is no ambiguity whatsoever. So inflation helps you resolve the horizon problem. And as we shall see later, this also helps you impose well-motivated initial conditions. And another, this is often referred to as Q greater than 1, you have power law inflation. It's just power law, right? That's all. And another possibility is when A is e power ht. Okay, where h is a constant. So let me call this as h subscript I corresponding to h during inflation. Okay, if h is a constant, and t goes from, be careful. When is A 0? T equal to minus infinity. So minus infinity to plus infinity. And this is known as de Sitter inflation. And during this epoch, this Hubble radius doesn't even have a slope. It's strictly a constant. Okay. And these, we often, you will study the inflationary models. There are inflationary models which lead to this, but there is a problem with such inflationary models. We'll talk about it. Okay. De Sitter has some issues. So we will study what is known as slow roll inflation, and we will not quite worry about how A of t behaves. We will deal with somewhat differently as we proceed. Fazlu, maybe I should answer your question now.
So the question is like, how can we make sure that the expansion is like exponential from this approach? For example, Q can be large or Q can be even 2 or 3, right? For making the...
I haven't come to that. I haven't come to how to drive inflation. I should talk about it before I end of my lecture.
So it's like we are imposing that condition.
I need to choose potentials that will give me the scale factor.
Okay.
All right. Okay. This is just to illustrate that some simple forms of inflation, can help you overcome the horizon problem.
Okay.
All right. It's more complex, I can construct V of phi, okay, that can lead to, I'm jumping the gun now. I haven't even said what is V of phi. Okay. But I presume many of you know, you can construct models that lead to this or other types of inflation. And we will see, given, what kind of fields and potentials will drive inflation. I just need a few more minutes to cover that. Just maybe one question, quick question. One quick question. Abhishek, you've asked. I will let him ask and I will come back to you later. Yeah. Go ahead.
Okay. So whenever we are referring to the causally connected region, we are referring to Hubble horizon. But
Hubble radius.
Hubble radius. So there are another type of horizon in cosmology called particle horizon. So why we are not...
But that's the future one, right? Okay. I look, the forward horizon, particle horizon, you integrate from 0 to t. Is that correct?
Yeah.
So, okay. I should talk about the particle, what you refer to as the particle horizon, what you will refer to as h of t, which is an a of t. I'm not explaining this dt by a of t. Okay. From some 0 to time t. I guess this is what you're referring to. Okay.
Yes.
So I should precisely talk about this. Now I have to explain to others, what is this? Why did this arise? I will try to do that. Okay. But what I'm trying to say is that in matter and radiation dominated universe, this is the answer I had provided earlier. The Hubble h of t is proportional to dh, modulo a constant. Okay. In inflation, there is an issue. They differ considerably. Time permitting, I will talk about it. Or we will talk about lunch or coffee. Okay. All right. Okay, so what do we need? We need to drive inflation. Okay, so what do we want? If we want a double dot greater than 0, I'm going to erase this picture now for want of space. Okay, I can erase this and write it again. Okay. So what do we want? We want a double dot greater than 0. Let me grab another chalk. And remember your two Friedman equations, a dot squared by a squared plus kappa by a squared equal to 8 pi g by 3 rho. And then you had 2a double dot by a plus a dot squared by a squared plus kappa by a squared is equal to minus 8 by gp. You can combine these two to write this equation. A double dot by a equal to minus 4 by g by 3 rho plus 3. The point is, if you want a double dot, to be greater than 0, you want rho plus 3p greater than 0. If you have matter and radiation, both rho and p are positive, there is no way, sorry, that has to be less than 0. Okay, that has to be less than 0 in order to achieve inflation. Okay, Of course, this cannot be achieved with matter and radiation, and you need to turn some exotic objects. And the exotic object we are going to turn to is our scalar fields. Right? Our scalar fields. So I need to give you some exercises, all right? So we will consider what are known as canonical scalar fields. I will write this. We'll focus on single scalar fields that is sufficient for our discussion, right? And what do we have? We are a scalar field in a curved space-time. S of phi is integral d4x root minus g, okay? Into what do we have? Minus half g mu nu d mu phi d nu phi, right? Minus v of phi. Okay, I'm trying to remember the signature, just bear with me. I think it is minus and plus. Okay, can someone help me with the action? Sorry, both are minus, right? Is that an overall? Okay, I believe so. All right. So now you can construct the stress energy tensor. I'm going to give you some exercises. You construct the stress energy tensor for the scalar field. Okay. And this is exercise, right? And remember, what are we have? We have phi to be a homogeneous field, right? We are trying to essentially drive this epoch of inflation, right, with the scalar field, okay? So what do we have? You have g mu nu is 8 pi g, t mu nu, right? And this t mu nu arising due to this field, nothing more. And the background, as far as we are concerned, is homogeneous. We have a Friedman metric, all right? And so we are assuming phi to be homogeneous. And what do you expect? You expect this t mu nu in our signature to be PPP, like the case of fluids that we had. But it will depend on the field and the potential, and you can quickly show rho is phi dot squared by V by 2 plus V of phi, and P to be phi dot squared by 2 minus V of phi. Okay? And if you want this condition to be satisfied, these are exercises. What do you need to show? Okay, there is another exercise I need to give you. Okay, I will mention that too. There are 3 exercises involving scalar fields you need to do. The first is, arrive at the equation of motion of the scalar field. Okay, and show that in the spatially flat Friedman universe of our interest, okay, in fact, it need not be spatially flat. This equation is V phi equal to 0. Okay, this is the equation of motion. V subscript phi hereafter will denote the derivative of the potential with respect to phi. Okay, let me repeat. You start with a canonical single scalar field described by a potential V of phi. Vary that to arrive at the equation of motion in a curved space-time. That's the first part of the exercise. Now, assume the space-time to be a FLRW universe and show that equation of motion is given by this expression. Calculate the stress energy tensor associated with the scalar field. Assume the scalar field to be homogeneous. And when you do so, the T mu nu will be of this form. Okay? It will be minus rho PPP, much like what we had in the case of fluids. They also describe a homogeneous, source of homogeneous background. And show that in the case of scalar field, the energy density is given by phi dot squared by 2 plus V, not surprising. Okay, a little more surprising is the fact that pressure is phi dot squared by 2 minus V. Okay, and what do we want? We want inflation. We want A double dot greater than 0 implies rho plus 3P greater than 0. So we just saw that A double dot greater than 0 implies rho plus 3p less than 0. I'm sorry. So what does it imply? Phi dot squared by 2 plus v minus, no, plus 3 phi dot squared by 2. What do I have? Minus 3v less than 0. So what is this? This is 2 times phi dot squared minus v less than 0, right? Is that correct? Okay. Or this is less than 0, or what do you want? You want phi dot squared less than v. And this is why, okay, this condition, is it will ensure inflation, okay? But often one works with phi dot squared much less than v, which is known as slow roll inflation. Okay? All right. So let me again summarize what I have done in this board. What are we doing? I hope you have understood why we need inflation. I hope you have understood how you cannot drive inflation. This is evident from the Friedman equation, the mixture of the Friedman equation, that you cannot drive inflation with the matter or radiation that you know. You need some exotic object. And the exotic object we turn to are scalar fields. And in the context of scalar fields, we take a simple canonical scalar field, but we are studying, you may have studied something like the Klein-Gordon equation or something. You may have done it in Minkowski spacetime, but you have to study a scalar field in a curved spacetime. And the action has to be covariant, okay? Action has to be invariant. So you'll arrive at a covariant equation, and you arrive at the generic equation of motion describing a scalar field, and in any generic curved spacetime, and then arrive at the specific equation in the Friedman universe, okay? And that happens to be of this form. Remember, the scalar field is homogeneous because we are assuming it depends only on time. That's what I meant. I should have clarified. Phi depends only on time. It doesn't depend on space. And the dots denote differentiation with respect to cosmic time, okay? And, the equation of motion happens to be this. There is another way of arriving at the same equation, is just the conservation law for this stress energy tensor, okay? If you use these expressions and demand that T mu nu semicolon mu is 0, you will arrive at this equation, nothing more, all right? And so you show that and arrive at these expressions for rho. Once we have everything on this part of the board, this part of the board is evident. You want A double dot greater than 0, which means you want rho plus 3p to be less than 0, which implies immediately phi dot squared is less than v. This is, it will guarantee inflation. But remember, I have erased that part of the board. You want to ensure that you have an adequately long duration of inflation so that the larger scale today, which is of the order of 10 power 4 megaparsec in length, is inside the Hubble radius during the early stages of inflation. Okay, and that sets the duration of inflation. You want to ensure not only do you have inflation, you want adequate duration of inflation. This is where the idea of slow roll inflation comes in. Okay, imagine you have a situation where phi dot squared is less than v. Okay, but very quickly the speed grows so that this condition is violated. That is not helpful. So you need slow roll inflation. And remember, I mentioned in the first overview talk that when I talk about the dynamics of a scalar field in an expanding universe, it is very much like a particle moving in a potential with a friction term. And that's what this is. This Hubble expansion, causes the friction, it slows down the field. So if you have a potential, and if the field is already slowly rolling, it will continue to roll slowly, and you want to ensure it is slowly loading for a suitable duration so that you have a sufficient duration of inflation. If it is not slowly rolling, if it is rolling faster, this term will slow down the field. So you are almost guaranteed inflation most of the situations, okay? But if you want an adequate duration of inflation, it is important that you also demand, slow roll inflation. And we will use these conditions to understand, given a potential, we'll construct something called the slow roll parameters, which will in turn help us understand, given some potential, which region of the potential or what values of the parameters of the potential can you have slow roll inflation? And we will construct solutions in the slow roll approximation for the background, and that will become helpful for us when we study perturbation. Thank you. I will stop here. Maybe I will answer one or two questions before I proceed. I am behind with my lectures, but I'm not going to speed up. The last lecture, I was always afraid it'll be, I may not have sufficient time to cover. I'm behind by about half a lecture or so, but I'm going to proceed at this pace. I will not try to speed up and catch up. I hope it is fine. I will be glad to answer one or two questions before we break for lunch. Abhishek. Use the microphone, please.
So the same modes that were present inside the inflation period, they were going out of this Hubble radius for some time period.
That is correct.
So, but they are again re-entering the.
That is correct.
So why are we not bothered about them?
There is no problem. We are imposing the initial conditions when they are inside the Hubble radius. They happen to go outside. I cannot help them. But that doesn't bother me. I am imposing that. What was our problem? Our problem was initial conditions. How do we impose initial? I kept drawing this picture, right? So think of this as a causally connected region, and you want to impose on something on this scale. I don't know how to do that. I cannot do that. If this is the region I can influence, right? How can I say something happened over a much larger scale? I cannot do that. Okay. So, but if this is the wavelength of the perturbation, and this is my causally connected region, right? Okay, I can impose well-motivated initial conditions. Let us say, okay, this is the standard example I give. I have equal, distribution of students, right? Imagine a situation that I have said something to you. In a very short period of time, someone at the other end knows what I have said. Is that feasible? It's not feasible. I need to allow for adequate amount of time for the information to propagate in order to ensure that person at the end, Raghavendra at the end, knows what we spoke about. All right? That's essentially the horizon. If you are within the horizon, I can influence what happens. Okay? I can tell everyone, what happened, and, I have information across this domain. This is the domain I can influence. But if you demand that, something happened over this domain, I don't have a causal mechanism to say something happened over this scale, within this scale, and over this scale. Have I made this clear? So it has to be inside. When I impose the initial conditions, they have to be inside the inside the causally connected region. Once I impose the initial conditions, I use the set of differential equation, or I write down all the differential equations involving perturbations in all the quantities in my universe and just evolve them. That's all. I just need initial conditions. Inflation provides you with those initial conditions. Yes, sir.
As we go into the future, more and more longer wavelengths will come inside our Hubble radius. So does it mean that we have to extend the graph towards the left also, and so the period of inflation should increase?
Yes. The answer is yes.
Okay.
So, but that time scale is so long. It doesn't matter for my life or your life either.
Yeah. But you have told that. Previously.
I should mention, having said that, there was this talk about measuring the changes in the Hubble constant. And people have recognized it is possible. Okay, I recall a paper by Matt Visser, if I'm correct. Okay, so what I said I should take back to some extent. People are also trying to see whether the constants are not constants, but are changing with time. Okay, so, but the answer is yes, but we are not so worried for the reason I just mentioned. I think that's a reasonably valid reason. Yeah.
Yes, so you wrote one, like whatever we had a very small slope, you told that in the de-Sitter case, it becomes the exact constant. So why don't we assume that's the case with our universe? Then even the expanding.
That's your choice. There are hundreds of potentials which will give me a variety of inflationary models. The data has to pick up. That's the first thing. Okay. I mean, it's not your or my choice. The data has to say that it prefers one inflationary model versus other. The de-Sitter limit has a peculiar problem that will become clear when I discuss scalar perturbations. There is no issue with tensor perturbations. With scalar perturbation, it becomes a singular limit. It's uncomfortable. Okay. So people consider slow roll inflation than de-Sitter inflation.
There is one question online. Why do we need scalar fields to explain inflation? Why not vector fields?
Okay. Good question. It has stumped me to some extent. I do not know immediate. There were some efforts to, if I recall the literature correctly, I think there were some efforts, but I'm just, concerned they may induce some anisotropy. I'm not able to immediately say a reason why we should not consider them at all. But for some reason, they haven't been able to be popular in the literature. And my only concern immediately is that they may induce some anisotropy. Yeah, I need to look at, I need to think and look at the literature to be able to comment about it. If they can remind me a lecture or two later, I'll be glad to answer them on Monday, for instance.
Okay.
Last question, possibly? Yeah.
So if we impose this slow roll condition to begin with, and given an equation of motion that says that there's some friction and phi dot will even continue to slow down, then when will the inflation end?
We will talk about it in the afternoon. Okay. We will see where inflation ends and so on. We'll construct something called a slow roll parameter that will tell us where inflation ends. Okay. And given a potential, you can determine that. We'll construct solutions for at least one or two models in the slow roll approximation before we take a perturbation theory. Okay. All right. Thank you. I'll see you in the afternoon.